In this video, we're going to take a look at the Radix sort. And this is another sort algorithm that makes assumptions about the data it's sorting. And in this case, the assumptions that it makes is that the data has the same radix and width. Now, what do I mean by that? The radix is the number of unique digits or values, in the case of characters, that a numbering system or an alphabet has. For example, the radix for the decimal system is 10, because there are 10 possible digits in the decimal system, 0 to 9. For binary numbers, the radix is 2, because we use 2 digits in the binary system, 0 and 1. And for the English alphabet, the radix is 26, because there are 26 letters in the alphabet. So that's what we mean by radix. Now, by width, I mean the number of digits or letters. For example, the number 1235 has a width of 4. The string hello has a width of 5. The number 10 has a width of 2. So 1235 or 1235 has 4 digits, so it has a width of 4. The string hello has 5 letters, so it has a width of 5. And the number 10 has 2 digits, and so it has a width of 2. And so the radix sort assumes that all the values have the same radix and the same width. And so that means that we can use the radix sort to sort integers and strings. The decimal point isn't a digit, and so floating point numbers can't be sorted using radix sort. So how does it work? Well, we sort based on each individual digit or letter position. And you'll see what I mean when we go through the algorithm on the slides. So we start at the rightmost position, and we sort based on that position, the digit or the letter at that position, and then we move to the rightmost -1 digit or letter, and we sort based on that, and we keep doing that until we've done all of the digits or letters and the values. Now, the important point here, and this is key, this is an absolute important point, is we have to use a stable sort algorithm at each stage. So when we sort the values based on the rightmost position, we have to use a stable sort algorithm. And then when we sort the values based on the rightmost -1 position, we have to use a stable sort algorithm. And once again, you'll understand why when we take a look at going through the algorithm. So let's do that now. So we have a different array here now at the top of the screen. It's got 6 integers in it, and you'll notice that they're all decimal numbers and they're all of width 4. They all have 4 digits. And so we can sort this array using the radix sort. So first we're going to sort this array based on the ones position. And so let's take a look at the first value, 4,725. The number 5 is in the ones position. And for the second value, 4,586, the number 6 is in the ones position. And so what we're doing here is we're sorting by the digit that has the least weight, because the ones position has the least weight in a decimal number. And so once we've done that, the bottom array will be the result. 1330 will come first because it has 0 in the ones position. That'll be followed by 8792 because there's a 2 in the ones position. Then we have 1594, 4725, 4586, and 5729. And if you look at their ones position or the rightmost digit, you'll see that the values have been sorted according to what's in that position. And now we move to the second position from the right, or the second least significant digit, and we sort based on that. And so at the top is the array we just had on the other slide, and now we're going to sort based on the second to last rightmost position. So for 1330, that will be 3. For 8792, it will be 9. For 1594, it will be 9. For 4725, it will be 2, etc. And so down at the bottom, we've now sorted based on that digit. So we have 4725 because it has a 2, 5729, which also has a 2, 1330 because it has a 3, 4586 because it has an 8, and then 8792 and 1594 both have 9s. Now, as I mentioned, critically important, this is a stable sort. And so you'll notice that we have a couple of pairs of duplicates here, 4725 and 5729 both have 2's in the rightmost digit -1 position, and you'll notice at the top that 4725 came before 5729, and in the bottom 4725 still comes before 5729, and that is critical. And that's because we have to use a stable sort algorithm. And the same thing goes for 8792 and 1594. They both have 9's in the second to right position. And in the top array, 8792 came before 1594, and it still does. And so that's critical. We have to use a stable sort algorithm. So now we're going to sort based on the hundreds position. So we sorted here based on the tens position. Now we're going to sort based on the hundreds position. And so when we do that, 1330 comes first because it's got 3 in that position, followed by 4586, 1594, 4725, 5729, and 8792. And once again, we have to use a stable sort algorithm. And so you'll notice here that we have 2 5's in the hundreds position, and 4586 still comes before 1594 as it did in the top array. And we have 3 values with 7 in the hundreds position, and the relative positions of those 3 values have been preserved. So 4725 still comes before 5729, and that still comes before 8792. And then the final step is we sort based on the thousands position. And so 1330 has a 1, 1594 has a 1, 4586 and 4725 both have 4's, and then there's 5729 and 8792, and we have sorted our array. Now once again, this had to be a stable sort, and so 1330 had to come before 1594. 4586 had to come before 4725. Now, maybe you can understand at this point why the sort has to be stable. If it wasn't stable, this radix sort wouldn't work, because at each stage, for example, in this last stage, if 1594 could cross 1330, we wouldn't get the correct sorted order. If 4725 could end up before 4586, we would not get the correct sorted order. And it's kind of interesting because when we first start doing the sort, it just means, you start to wonder, well, how is this ever going to work? Because when we sort on the ones position, if we go back there, we got a certain array, but then when we sorted on the tens position, all the elements are changing positions again, and you're wondering, how is this ever going to end up in sorted order? But the key is we're sorting from the least significant digit, the one with the least weight when it comes to the value, to the most significant digit. And at every phase, it's a stable sort. And so because of that, as we move from right to left, as we go from the least significant digit to the most significant digit, you'll see that a sorted order is starting to emerge. And then on the final step, because it's a stable sort, all of the previous sorts that we've done still count. They don't get undone at each stage. It kind of looks like we're not sorting at each stage, but we are. The data is gradually becoming more and more sorted. And the fact that we're using a stable sort algorithm means that on that final sort, when we're sorting on the most significant digit, values that have the same most significant digit will not switch relative positions. And so the values that have a higher digit in the hundreds will remain after values that have a lower digit in the hundreds. And the same will go with when we do the sort with the tens. When we do the sort based on the tens, values that have a duplicate tens value, well, the value with the higher digit in the ones position will come after the value with the lower digit in the ones positions. And so you can see that because we're using a stable sort algorithm at each phase, and we're going from the least significant digit to the most significant digit or letter, depending on what we're sorting, the results of previous sorting phases are preserved. And that's why radix sort works. All right, so counting sort is often used as a sort algorithm for radix sort. Now, in the last video, I said that the implementation I showed you was not stable. So when we implement radix sort, you'll have a chance to see the stable version of counting sort. Now, once again, because radix sort makes assumptions about the data, we can achieve linear time. Even so, this often runs slower than O to the n log of n because of the overhead involved. And by overhead, I mean that you have to isolate each individual digit or letter at each phase, and so there's overhead involved just to figure out what value you're supposed to be sorting at each phase. And because of that, even though it can achieve linear time, it often runs a little bit slower than that. Now, whether or not it's in place will depend on which sort algorithm you use, because as we've seen, some sort algorithms are in place and some aren't. So radix sort can be in place, or it might not be in place. It's going to depend on what sort algorithm you choose to do the sorting at each phase. It's a stable algorithm. As we've seen, because the sort algorithm we use at each phase has to be stable, radix sort turns out to be stable. And in fact, that's key to making it work, is that the sorts in earlier phases aren't being undone as we sort based on the more significant positions. All right, so that's it for the theory. Let's move on to implementation. I'll see you in the next video.